Welcome to this lecture on Newton's third law. Newton published a statement of the third law in his book titled Principia in 1686. The original statement from Newton was in Latin. The English translation of that is, to every action there is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. The part here, two bodies, is extremely important. The action is acting on one body and the reaction is acting on another body. So what are the action and reaction forces? Let's explore. Let's say you have a donut on a plate. You can keep a donut on a plate and it will hold its shape, but you cannot keep a cup of water shaped like a donut on a plate, because the molecular bonds in the donut are much stronger than the bonds in water. And these molecular bonds hold the donut together. If you consider two tiny pieces of mass in the donut, the masses are M1 and M2 inside the donut. When we try to pull the donut apart, that is, when an external force tries to pull the masses away from each other, internal resistive forces F12 and F21 keep the masses together. The resistive forces, as you can see in this diagram, F12 and F21, they're equal and opposite. And these resistive forces, F12 and F1, ultimately create the action-reaction pair of Newton's third law. When the external applied force is removed, then F21 and F12 will also disappear. So here we have a donut with no external force, and there are no resistive forces inside the donut. But when we apply an external force, F and F, the donut stays in equilibrium, but the internal forces are invisible. To see the internal forces, you will have to cut the donut. The cut is not an actual cut, it's an imaginary cut. And the resistive forces P1, P1, P2, P2, which are equal and opposite, they appear across the cut. So these forces P1 and P2 are the integrated values of the resistive forces of all the masses at the interface. So this cut is imaginary, and when you have the imaginary cut, you begin to see the internal action-reaction pairs of forces that are resisting the donut from falling apart. The imaginary cut reveals the action-reaction pairs of Newton's third law. Let's look at some other problems. For example, here we have a bucket, and inside the bucket we have three circular objects. The circular objects are in contact with each other and also are in contact with the walls of the bucket. The weight of these objects are W. So, to see the internal action-reaction pairs of forces, we will need to separate these circular objects. So here we have separated the lowermost circular object. So here is the lowermost circular object. Its weight is acting downward. The wall at B is pushing the object to the right. The floor at A is pushing the object upward. And at the contact C, this object is applying a force C on our first circular object. Similarly, if we separate this circular object, we will see the action-reaction forces C and C. So this C is the push from the upper object on the lower object, and this C is the push from the lower object onto the upper object. This is the weight W, and this is the force D coming at the contact D between our object and the wall of the bucket. Similarly, if we go to the topmost circular object, we will see an F, which is coming from the wall of the bucket, weight acting downward, and this E and that E are the action-reaction pairs. The top circular object applying a downward force on the middle circular object, whereas the middle circular object is applying an upward force E on the top circular object. At B, this is a force from the wall on this object, and this B and that B are the action-reaction forces. The wall is pushing the object to the right. The object is pushing the bucket to the left. Similarly, this D and that D, they're action-reaction pairs. Wall pushing the object to the left, object pushing the wall to the right. Similarly, this F and that F are action-reaction pairs. The wall is pushing the object to the right, the object is pushing the bucket to the left. Let's look at another example, which is a little more complex. This kind of a structure that we see here is called a truss. So we have three rods connected with pins, and it's supported here, and we have applied a load P. This pin A is applying two forces, AX and AY. This roller at C is applying an upward force CY on the truss. If we separate all the pins and the rods, then we expose the internal action-reaction forces. So this AX and AY, they remain. The action-reaction force between this pin and member AB is this FAB action-reaction pair. The action-reaction pair between this rod and that pin is again FAB action-reaction pair. Similarly, pin with BD, and you can see a whole bunch of action-reaction pairs here, here, FBC, FBC, FCD, FCD, FAD, FAD, and all of these action-reaction pairs are keeping this structure together. Thank you for watching.